Okay, everyone, let's start where we where we have stopped in the last class. Am I audible to you?
Sir,
Okay, fine.
sir.
Okay, let's continue from here. Okay, so earlier we have discussed about the ILD for simply supported beam. Okay, now we are going to discuss about the ILD for cantilever beam. Okay, so let's go through this. First, what we need to consider, there are some condition within this. So we will consider the first condition as using ILD to calculate SF and BM at a section due to single point load. Okay, here you see there is a single point load W is given. So for that single point load, we are going to find out this. Okay, so in the figure, it is showing a SSB carrying a moving load W at a distance X from support A. C is a section at a distance Z from support A. So here you see figure B and figure C are the representation of SF and BM for that section C, as we have already did in the earlier part. How we have calculated all this calculation we did earlier. So just simply drawing that. So here you see Y, this Y, and Y dash, this Y dash. Coordinate of ILD, these are the coordinate of ILD for SF and BM at that given load point. So therefore SF due to given loading position is given by nothing but W into Y, and similarly bending moment is given by W into Y dash. This is for single point load. Just remember the terms. Okay, we only need these terms. Just remember the term, what are this condition, and according to that what are the loading position. Okay, similarly when we consider more than one point load, so here you see we are considering four loads: W1, W2, W3, and W4. There are 4 point load we are considering. So similarly, what is the SF is given by? Very simple. W1 into Y1 plus W2 into Y2, W3 into Y3 plus W4 into Y4. This will give you the shear force for that point C for this all point load. This 4 point load you will given by this. Okay. Similarly for bending moment, again same. W1 into Y1 dash, this Y2 dash, Y3 dash, Y4 dash. Okay. Let's remember the terms. No need for the derivation of all these things. Let's remember the terms. We are going to use this while we solve the numerator. Okay. For easy understanding, I will give some example in the later part. Here you see, here is a simple example how we need to calculate. We are considering a beam with 3 point load 40, 60, and 80. Okay. 3 point load at different distance, as you can see 2 meter, 6 meter, and 8 meter, and total span of the beam is 10 meter. This is just for example for understanding. Okay, so here you see how we need to find out determination section and draw ILD. Okay, what we need to do, calculate the maximum values of SF and BM at that point C, at this point. Okay, so for that we already know there's two equation FC for FC. One is L minus Z by L and one is minus Z by L. Okay. So see what is the distance of L. L we know 10 meter. What is the distance of Z? Z is nothing but it is the distance from the point A to the point C. It is at the distance of 4 meter. So just put this value 4. Just simply calculate. You will get two FC values 0.6 and minus 0.4. Similarly, we need to use this MC formula, L minus Z into Z by L. Everything you know, just put the value, you will get this MC value. Okay. Up to this, it's very simple. Just remember these three formulas. You can easily put and you can find. Okay. But after this, what we need to do? We need to find out this coordinate y1, y2, these things. Okay. So how we will calculate? Here you see calculation of coordinate. This first one you need to know y1. So for this, what you need to do? You need to do or you need to consider. I think all of you know the similar triangle formula. Okay, for similar triangle, what we need to do as per the triangular formula, you can easily find out this coordinate. The condition is AAA means all the angles are equal. Three angles. I think all of you know this how to solve. If you consider this is the okay, there are three loads here. You see 1, 2, 3, 40, 60, 80. 40 is in the left side and 60 and 80 is in the right side of that point C. So here you see, if you consider this point as C, this 0.6 and 0.4 we have already calculated. This 0.6 and this 0.4 we have already calculated. So we have drawn this 0.6 and 0.4. Now what we need to do, we need to calculate this y1, this y2 and this y3. So for this, what we need to do, we need to use the similar triangle formula which you have already got in your school level itself. So for that, if we consider, here you see, if we consider this first portion for finding out this y1, this first portion, here you see we have drawn this. By considering that first portion, we have drawn this. Here you see this distance we already know 0.4. This y1 we need to find out the distance from y1 to that point A. It is also known to us, it's 2 meter, and that C at a distance 4 meter for that point A. So if we again see, when you do, you no need to draw all these things and do everything, but for your understanding, here I have shown you the all the steps how you have to calculate this y1. Okay, so after this, if we break harder, you will get two triangle like this. See, from this, okay, from this, if we break this triangle into two part, you will get this two. There is a one similar smaller triangle in between the bigger triangle. So there will be two triangle. One is this, one is this. So if now we use the similar angle condition, what we will get? You can simply write y1 by 0.4 is equal to 2 by 4. This. I think all of you understand this. All of you know this, how you need for using the equal angle triangle condition. There are some conditions I think all of you got in the school level. When you say this all two triangle is similar triangle, for using this condition, we can easily say that y1 by 0.4 is equal to 2 by 4. So for here, from here, if you simplify, you can see easily say what is our y1. Hello, is it clear? Is it clear? Okay, fine. So similarly, you can easily find out this y2 and y3. How? For now, what we need to consider? We need to consider this triangle. See, I am drawing here. It may not be straight. Okay, I'm just showing you. Okay, for y2, it is in the upper side. This value is given 0.6 we need to find out this y2. Okay. Similarly, what we need to do, we need to consider y2 by 0.6 and the distance. Here you see, it is at the distance. For finding out this y2 is at the distance. From here, you need to consider. Similarly, just put this y2 by zero point 0.6 is equal to 2 by 6. From here, you can easily say what is your y2. And similarly, when you find out y3, you can easily say is what distance your y3 is. Okay. I think there is a mistake. This should be 4. Okay, not 2. It should be 2. It's 5 y3. This is your y3 is at a distance. Y2 is at a distance of 4. So 4 by this distance, it is 6. So y2 by zero point 0.6 by 4 by 6. So this must be 4. Okay. And here it's fine. Y3 is equal to 2 by 6. So for here, from here, you can easily find out this y1, y2, and y3. So our one part is over. Calculation of the coordinate. Okay. Next, what we need to do, this. We are considering the bending moment, SF and BM at the section due to moving ideal load using ILD. Up to this, is it clear to all of you? Okay, fine. Let's move to the next one. These are all the same things. Just we are considering now UDL. Earlier, what we did, we considered that point load. Now we are considering as UDL. This UDL W. We are considering a UDL. Okay. Same way, we need to consider the distance and all these things. All the span is given. For this, when we consider UDL, this things will be same. Okay, it will not be sense. These two value will be same. Just the differences here we need to show. Figure A shows a SSB carrying an UDL, W per unit length. Figure B and figure C are the ILD for SF and BM at the section C. Their SF at the section C due to the UDL is equal to, here you see the difference. Earlier what we did, for that finding out that shear force, we can simply say that it is, when in case of point load, it is simply W into Y. And for bending moment, it is W into Y dash. Okay. But here, you see, in case of UDL, what we need to do, for SF, it is given by W into area of the shaded portion in ILD. Means this shaded portion, okay. And for bending moment also, MC is given by W into area of the shaded portion in ILD for MC, this shaded portion. Okay. You need to remember only these differences. Okay. How we need to consider in case of point load and in case of UDL. What is the difference to finding out this shear force and bending moment? So here is a see example. If we consider an example, then it will be easier for us to understand. Okay, similarly, we are considering a beam of 10 meters span, AVL of 20 kilometer per meter, at a distance starting from 2 meter and ending at 6 meter, mid portion at 4 meter at the point C. So we are considering a simple this beam. So for this, what we need to do, similarly, again using the same formula, you need to find out this FC, L minus Z by L, or FC minus Z by L. This will be same. And similarly, MC is same. You need to find out. Now, again, we need to find out the coordinate. This coordinate, again, you need to find out by using the similar equal triangle formula, that condition. By simply this way, you can easily find out this y2, y1 dash, y2 dash. Similarly, you can easily find out. Now, see, the basic difference is here. For SF, what we need to do? This. For SF, what we need to do? We need to consider this as the shaded portion area, as here it is said, area of the shaded portion. For finding out that SF and for finding out the moment also, area of the shaded portion we need to consider. So here you see area, there is two area. Here you can see there is two area. One is this shaded portion in the above, and the below there is one shaded portion. So both for this two shaded portion, what we need to do, if we take out this shaded portion, how it look like? It look like something like this, is it? And it is nothing but it is a rectangle, is it? So what we know, what we need to do for rectangle, I think all of you know how we need to calculate the area. Can anyone say me how we need to find out the area of a rectangle? Please speak. Okay, anyone of you, please respond. If we need to find out the area of a rectangle, how we need to do that?
Length into breadth.
Is it so? For
Area, right?
for
Sir.
rectangle, not for this is not the equal side. Okay, it is given here. You can see here.
Sir, that one is for area for triangle, no sir? Half into base into height.
Yes, sir, that's what triangle, sir.
Please give me a second. Okay? Okay, sorry, there's a mistake. Okay, this is not a rectangle. I think I am saying it's wrong. It is a trapezium. See this structure, this trapezium, and for this below trapezium, we need to calculate these two. Okay, it's look like something like this. Is it for the above portion, and for the below portion, it is something look like this. So we need to consider these two, this one above and the below one. Both these two trapezium we need to consider, and for that, can anyone say me what is the formula? How we need to find out this area? It is given by what? Half into
Sum of parallel sides into
yeah sum
cantilever.
sum of the parallel side, then
into height.
yes height. So here you see we are using that formula for finding out this area. Okay, sum of the parallel side. There are two parallel side. What is this two parallel side? This one is and this. This we already know 0.6 and y2 we have to calculate. Similarly, below we can say 0.4 and this y1. This is the parallel side. So just use that and find out this area. You will get one area for the one above, and for the below also you will get one area. Similarly, for bending moment also, after finding out this y1, y2 dash, you can easily say find out the area for that trapezium also. Okay, for this portion, for this shaded portion. Okay, use the similar triangle formula for finding out this y1 dash and y2 dash. Okay, I'm not showing you the how to find out this y1 and y2 dash. It is same. Here you see y1, y1 dash, y2 and y2 dash. You just try like this. It is already showing here how we have calculated this y1, y2 dash, y1 and y2. After finding out this, use the trapezium to find out the area for the shaded portion of the above and for the below part. Above means for this ILD for FC and ILD for MC. Take the shaded portion, and for that shaded portion try to find out the area. So see, we have calculated four area A1, A2, A1 dash and A2 dash. Okay, after finding out, first what we need to do, we need to consider the beam as per the sorry, as per the length given, and according to that length we need to consider one portion at a time, and for that portion you need to calculate the ordinate, these ordinates, y1, y2, y1 dash, y2 dash. Okay, after finding out that ordinate, you need to find out the area of the shaded portion. And remember this, when it is given in terms of UDL only, you need to find out the shaded portion area. Why? Because UDL is not at a point, it is uniformly distributed over a span. Okay, so for that span, that UDL effect is given in terms of that area, because UDL is applied in that particular area. So we need to find out that area as by using this formula. So after finding out this area, what you need to do, here you see as given in this formula, SF is given by W into area of the shaded portion in ILD. So what we did, see, SF at C, W into area of that shaded portion. Okay, here you see SF at C. W we already know it is given 20. Area we have calculated this one A1 and A2 0.6 and 1 0.6 is minus. So just put this value, we will get this SF at that point. And similarly for bending moment at C, simply W into area of that shaded portion. We have already calculated A1 dash and A2 dash. Just put this value, you will get this bending moment at that point. There is a one basic difference between this point load and this UDL. The difference is in point load, we no need to consider the area because it is acting at a particular point. But when we consider UDL, we need to consider that area where the UDL is applied. Okay, these are the two basic. This is the basic difference between this point load and UDL. Is there any doubt anyone have?
Sir,
Yes.
like, why don't we use why don't we follow the steps we used before? Like, just find arrow A, find arrow B, and easily we can just find bending moment at any point. You know, if we know arrow A and arrow B, then we can just find, because this one is, because now we have to find shaded portion. And so if we can, we use the other step where we can find arrow A, arrow B, then we can find bending moment or shape us at any point if we know our area and arrow B easily.
Yes, you can also do that.
Or
Okay.
we
Okay, you can also do that. But here you see, it's for that you need to consider reaction on all these things. Calculation is little bit long, but this if you use this way, because for ILD you can already you say that FC is given by this formula. You need to remember this formula. L minus Z by L and minus Z by L. These two for, let me show you, for this type of diagram. Okay, for this diagram, and for MC also the formula is fixed. This formula. So if you know all the distance, you directly say your FC and M bending moment. So after that, if you calculate the ordinate by multiplying and by finding out this area, you can easily say what is the SF at bending moment and SF and bending moment at that particular point. This is the different way. You can also use that way also. Okay, but while doing ILD, you need to use this formula because these formulas are given for ILD. For simple calculation, for whatever you say in the earlier case, you can also use that also. But when you need to draw ILD, you have to use this formula because these are the formulas given for calculation of ILD. Okay.
Yeah, sir, hello, sir.
Yes.
Hello, sir. Can you show that the bending moment diagram for this load?
Yes.
The can you show the ILD for this question, the bending moment?
For this,
Yeah, sir. Can you the ILD, the diagram for this question?
yes. See, ILD and shear force diagram will be like this only. This, this is the basic diagram.
Yeah, sir. This one, sir.
Yes.
Sir,
Just
but
you.
sir, look at
Just
this.
this is the bending moment diagram.
Sir, this bend. Sir, but it should be parabolic under that UGL load. It should be parabolic, but it's still inclined
No, no. See, we are
because
just
bending moment. If we have UDL, the that place should be parabolic, and
for, for,
if it point load, it should be inclined. But here it's still inclined
for the
under the load.
for
It
the
is parabolic load.
yes, for the UDL you are saying, na?
Yes, sir. Under the UDL, that part it should be parabolic.
Yes, yes.
The diagram, but here it's still inclined.
Okay, you see, when we solve one numerical, we will solve one numerical. Okay, after some time. So when we solve the numerical, you will understand. Just wait for that. Okay, I will explain there what
Okay, sir.
actually comes. Just wait for some
Okay,
time.
sir.
I'm going here. Michael. Okay, what you have asked, I have already, I understand the question. Okay, you are saying that for UDL it should be parabolic and for point load it should be inclined. Okay, but see what we are doing only for that particular point C. We are only drawing for that particular point C. Everything we are calculating for that point C. Okay, so whatever we have calculated only for that point, the impact of all the loads as it is point load or that as it UDL load, we are only doing for that point C. Okay, so for that point C only we need to draw. Okay, so here you see one more example I have given. Here one example is given. This is the C. It is the combination of point load and UDL. Here you see this is the combination of this point and UDL load. There are 3 point load and 1
Okay, okay.
UDL. Okay, so here you
So,
see.
sir, that means when
Yes.
sir, that doesn't mean that that means when we are doing this area,
Yes,
we're
yes,
converting this UDL to a point load at that
yes,
point.
yes, oh, yes, yes. Basically, is this we are considering every
Okay,
load
sir.
and converting into to that particular point. Okay, you are saying the correct thing. That means we are converting that UDL to a point load. That's why we are considering that
Okay, sir.
area. We have calculated that area. Na? That's why we have calculated that area so that we can say what is the impact of that area in that point, particular point. Okay. So,
Yes, sir. Yes, sir.
okay,
Understand.
here is one more type of example. Okay, you see, let me check the time. How much time is there? Okay, we can. I think your next class will start at. Excuse me. When is your next class will start? It's 11:15. Okay, all of you give me your
11.
attendance. All of you give me your attendance in the chat box. I think we need to stop here. Okay, we will continue in the next class. Okay, let me stop here. All of you, please quickly give your attendance. I think your next class will start at some time. And everyone, let's stop here. We will continue in the next class. Thank you all. Okay, see you in the next class.